We are here at the Kalos offices, and we're going to talk about one of my favorite topics because it's one of the ones that creates some of the most angry social media arguments. We'll get to what that specifically is when we get into the middle of it. So let's see if you can catch on to where that occurs. But we're going to be talking through breakers, wires, otherwise known as conductors, fuses, and overloads. And specifically NFPA 70 is a lot of what we're going to be talking around. NFPA 70 is the National Fire Protection Association 70 guide, which is also known as the NEC. So NFPA, National Fire Protection Association, it's association, right? Association, yeah. Sounds right.
Sounds good.
Is the organization that actually creates the electrical code. And the reason is because one of the primary reasons we need an electrical code is so that we don't burn down the house, quite literally. Yeah, I don't know who sings that song originally, but it's a good song, really good song, great lyrics. It was actually, that song was also written by NFPA, actually, believe it or don't. So, two different segments that we're going to be going through if you want to look it up, and the reason why I do this right off the bat is that anything that I say, if it's incorrect, follow what the NEC says. I'm covering specifically how it relates to air conditioning, specifically mostly focusing on residential and light commercial, but it does go into some of the larger stuff. When you go into really big stuff, a lot of the things I'm going to be talking about as far as what's on the data plates are quite a bit different, and so that's where sometimes I'll get a little bit of pushback. But ultimately, you can go and check for yourself by going to 310.15, specifically table B16. So brackets B, brackets 16. If you Google that, you'll pull up like 1,000 of them. That is the wire sizing, the conductor sizing segment of NFPA 70. And then section 440 is specifically for air conditioning. So there's a lot of kind of unique things, that little nice, easy exceptions that we get in air conditioning that makes, in the end, makes it a lot easier, but also creates a lot of heartache when professional electricians don't pay attention to section 440. And they try to apply the other NEC standards without looking at 440, and they think we're doing it wrong, when in fact, actually, we're usually not doing it wrong. This is one case where often AC guys actually aren't doing it wrong, surprisingly. Start with circuit breakers. What makes a circuit breaker a circuit breaker? What makes it different than a fuse? Aaron, I'm going to be turning to you a lot today. I don't want to make JD. I don't want to make JD nervous.
That very early.
What makes a circuit breaker a circuit breaker?
Can you manually open the circuit?
You can manually close it usually. So it opens the circuit just like a fuse or a fusible link. Fuse is just short for fusible link. Means it actually opens the circuit and then stays open. A circuit breaker is generally that means resettable. I don't know that that's a universal rule, but when we say it, that's what we generally mean. Yeah. I don't know why I don't call on JD because he did get the highest EPA score of anyone I've ever tested.
I'm still missing one.
You're still missing one of them?
Not universal.
Yeah, you just lost it. You just she just up and runned away, runned off.
Keep dang it.
Yep. So right off the bat, I made this illustration because, and you know, of course, if you're doing this professionally, you already know this, that a tripped breaker and an off breaker are not the same thing. A trip breaker is going to go into the center position. Sometimes they're going to have a little window, sometimes they won't, but they have to be completely reset and then turned back on. We talked about this 2 weeks ago, but I want to cover it again quickly. Under what circumstances does a breaker trip? What causes a breaker to trip?
Short.
A short? A short is what, again?
Whenever the intended path takes a undesirable course that shortens the length of it.
Okay, you said a lot of extra words there, but you kind of got to the point. You know, it's good. It's good. A lot of fancy talking there. Yeah, so it's whenever there's a path of lower resistance than the design. So, and again, there's a lot of different ways of saying this, but electrons move from areas of higher potential to lower potential, higher voltage to lower voltage. In other words, there has to be a potential difference. And so, generally speaking, when we're creating a power supply, or not generally speaking, really always, there's always going to be two sides to that power supply. If we're talking about, you know, a 240 volt appliance, it's the two legs of 240, 120 on each side, right? If it's a 120 volt appliance, it's going to be 120 volts to neutral. If it's a battery, it's going to be the two sides of the battery. If it's a transformer, it's going to be on the secondary side, it's going to be your common and your hot on the other side. And so those electrons move in between those two sides. And in order for them to have controlled current, they have to go through a proper amount of resistance. If that resistance is too low, it causes high current, which then trips the breaker. So how much current is going to trip this breaker right here? How much current is it going to take?
30.
30 of a current.
Yes.
30 of a current.
30 amps.
30 amps. But here's the trick question. If we had a breaker like this one, this is a square DQ02 pole, and we were running a system that was drawing 30 amps, how long would it take to trip? It might never trip. Now, it should eventually, if we're drawing just a little bit over that, 31 amps, it should eventually trip. But is it going to trip right away? No, it's not. And so we have to make a quick distinction between things that trip breakers, blow fuses, go out on overload instantaneously, and things that trip breakers, blow fuses, go out on overload over time. Because those are two very different categories of problem, generally. A short circuit is generally going to cause this breaker to trip how fast?
Right away.
Boom, right away, right? You got a breaker that's tripping, you reset it, bam, it trips again, and then you just keep resetting it, right? Isn't that what you're supposed to do? Yeah, yeah. Yeah, it's good, because if that compressor is shorted internally, now you're just creating more and more carbon and acid and sludge inside that compressor. It's great.
That's what we want.
Just keep resetting that bad boy.
That's what we want.
And just hold it in place. Try to hold it. No. So once a breaker trips, don't keep resetting it. And if it instantaneously trips, you're looking for a short circuit, specifically, most commonly, a grounded condition. That's the most common, but you can have a leg-to-leg short as well. All right, a lot of different types of fuses. I don't expect you to memorize anything on this screen, but just kind of showing there's a lot of different types of fuses. We have your, your mini ones that we see in a lot of automotives. We have the, the ATO is the standard kind of blade type fuse that we use in air conditioning. There's a whole bunch of different types of fuses, but they're all going to have a rating on current, and they're generally also going to have a voltage rating. Now, what is that voltage rating on a fuse? What does that represent? Sam, voltage rating on a fuse. Why is there a voltage rating on a lot of fuses? It's usually pretty high, too.
Because voltage doesn't blow a fuse, amperage does.
Amperage is what blows a fuse, right? The current is what blows a fuse. But why do they have a voltage rating? Because there's a point at which you may not even have overcurrent, but you have high enough potential that the clearances, the tolerances inside of that fuse could cause an arc. So each fuse has a little different insulation rating and all that. So you wouldn't want to use a fuse that was rated for a maximum of 250 volts or something on a 480 volt circuit or something. It's not that, it doesn't happen very often, but it is something to consider with a fuse. But there's another thing with fuses. Another big difference in fuses. Does anyone know the difference between these two fuses, for example? I mean, you can't always tell just by looking at them, but there's some kind of giveaways here.
He does. He does.
Who? You do? What's the difference?
One is a quick blow and one is a slow blow fuse.
Quick blow, slow blow, right? Now, I'm not saying that that's always universally, that's how they're going to look, but you have some fuses that when they get to their rating or above their rating, they're going to blow really quick. And you have some that are designed to not blow up quickly on purpose. So the amount of overcurrent dictates the speed that it's going to trip, right? But also the type of fuse dictates how quickly it's going to trip. So on a fast blow fuse, and again, like I'm sure there's some rating out there that tells you exactly the amount of time based on the amount of overcurrent. There's probably some table somewhere. We don't care. The main thing you need to know is that you don't want to replace a slow blow with a fast blow or a fast blow with a slow blow because they do different things. The fast blow needs to protect electronics, for example. You don't want it to run even a short period of time at overcurrent. But if you have something like a motor, anybody know what type of load a motor is? What's the name for that type of load? Anyone know? Sam?
Inductive load.
Inductive load, right. Motor is a magnetic load, and in an inductive load, the current starts out higher. So you have those start amps. And why does the current start out higher? Does anybody remember why? Why does the current start out higher in a motor? Yes, Sam?
Inductive load creates its own resistance.
The inductive load creates its own resistance, which is called what?
Inductive resistance.
Inductive reactance. Very close. Max knows the answers to all these things. I see him back there smirking. Inductive reactance. So it's a type of resistance that builds as that motor gets up to speed, right? And a kind of a related concept is back EMF or counter EMF, counter electromotive force. That counter EMF is what creates its own resistance because a motor also acts as a generator once it starts getting up to speed because it has these opposing magnetic fields. But the point is when it starts up, it has high current. And if you were designing everything so that way it tripped properly when it was at running amps, then it would always be tripping at starting amps. Always be tripping. Straight up tripping, yo. Woo, good times. All right, short circuit, we already covered this. Short circuit, so we're going to kind of go over some quick, dictionary definitions, if you will. A short circuit in a device, an electrical circuit of lower resistance than that of a normal circuit, typically resulting from the unintended contact of components and consequent accidental diversion of the current. Fancy words to mean something touching something ain't supposed to, right? An open circuit is what? Something ain't touching when it's supposed to. Exposed is, how do you spell exposed, Aaron? S-P-O-S-E-D. Okay, exposed. That's how you spell that. All right, so overload is to place too much load on. Pretty easy. It's like, it's like running a truck and you fill it up with too much, rock in the back of it. It's not, there's nothing necessarily wrong. Well, I mean, it is a key distinction because there's not anything necessarily wrong with the truck. It's just you put too much on it. So to overload a motor, for example, means you put too much load on the motor. The motor is trying to turn against too much resistance, physical resistance. Interesting thing about motors, though, is what happens to the electrical resistance in a motor. I'm going to dwell on this one for a second because it's one that it really is hard for people to get their head around. What happens to a motor's electrical resistance when its physical resistance is increased? So when the amount of force that the motor is working against is greater, what happens to the electrical resistance inside the motor? Anybody care to take that one? Max? What's that?
Decrease.
It decreases. Why does it decrease? Why does the electrical resistance in the motor decrease when the physical resistance against the motor increases?
It's not spinning as fast.
It's not spinning as fast. And when it's not spinning as fast, it's not producing as much back electromotive force, counter electromotive force. So it's acting less as a generator. When it spins slower and it acts less as a generator, it produces less of its own voltage. So therefore, it has less of that inductive reactance, less of that resistance that the motor creates when it gets to full speed, right? So as a motor spins faster, it creates more electrical resistance. As a motor spins slower, it creates less electrical resistance, and that's why it draws more current, right? More electrical resistance equals less current. This goes back to Ohm's law stuff, but sometimes we struggle with this because we get physical resistance confused with electrical resistance. Those are inversely proportional in a motor, in an inductive motor. Getting any of that, Mario?
Every word of it.
You're giving me that deer in the headlights look, but I appreciate it. It's okay. All right. So when we say overload, we can just mean to place too much load on. So how could you overload a compressor? We talked about this for the last couple weeks. We've talked about this. How could a compressor be overloaded? Could it be too much refrigerant? Sure.
I mean, that wouldn't create an electrical overload because that would slow it down. Are we talking overload mechanically or electrically?
We're talking about, because they're actually both the same in this case. So you overload electrically when you have too low of electrical resistance and therefore too high of current. So in this case, load and load are proportional. It's the resistance that's inversely proportional.
But if you were overcharged with refrigerant, you would be adding physical load,
correct,
which would reduce
your electrical resistance, which would increase your current.
Yes.
Yes.
Not resistance, load.
Right. Correct. So resistance, electrical resistance, and physical resistance are inversely proportional. I'm not going to smile. I'm not going to smile. It's okay. Overload conditions with physical overload and electrical overload as far as too much current, those are proportional to each other. So with a compressor that's just come out of defrost, the system that's just come out of defrost, what happens to your suction pressure in a system that's just come out of defrost and the evaporator coils are all really warm? Your suction pressure is really high, right? So you could potentially have suction pressure that's so high. So when suction pressure is high, what happens to your refrigerant density in your suction line? Is it more dense or less dense? It's more dense, right? Higher pressure, more density. So more refrigerant is coming into that compressor. What happens to your compressor current when that happens? Goes up, right? We talked about that. So, does anybody know what this thing in behind these words is called? It's not a very great picture. But what are these called? You don't see these in residential, by the way. This is a commercial thing. Commercial industrial. No. This is called a starter. So if you ever hear the term a starter is just a contactor and an overload mashed together in one unit. So it actually can shut down a particular individual component based on the current being too high, overloading. So it's basically like a contactor and a circuit and an adjustable circuit breaker put into one component. And you'll see that a lot in bigger units, and they call it a starter, which is an annoying name. It's a really, it makes you think it's a start capacitor or something, at least for me, but it's not. All right, ground fault. We're defining a lot of terms right now, so that way this all makes sense. Because when you get into the NEC, like it becomes kind of important that you understand the differences between these things. Ground fault. The momentary, usually accidental, connection of a current-carrying conductor to ground or other point of differing potential. It's very similar to a short, but specifically it relates to a certain type of electrical fault. And that's especially when you have a circuit that has a GFCI. Have you ever heard of that before? GFCI or GFI? They have little buttons that you reset that always trip all the time in the bathrooms and the garages. That's ground fault circuit interrupter. So that specifically, those are specifically designed to look for imbalances on the legs, on the two legs. And if there's an imbalance in current, that means that some of that current is leaking to ground, to some other path. And that can be unsafe. So we have insulation breakdown and all that. Now, specifically with ground fault in the NEC, National Electrical Code, the 2020, I believe it's the 2020 NEC, specifies that we're going to have to start having GFCIs on condensers. And that's going to be a very interesting, you want to talk about a new form of nuisance call, it's going to come up a lot. In the same way that, you know, ground faults trip in garages when people, you know, hook up their old refrigerators to them, we're going to start running into that. Did you just say wait?
GFIs have to be on the system?
They're going to be most likely in the disconnect or in the breaker that feeds the condenser.
Not the air handler?
So it's
I
got to
don't
be
think
connected?
so. There's some reason why, and I don't remember why.
So the 240 has to go through the GFI,
Yeah.
then disconnect, and then system?
Well, it's going to be integrated into this. It's going to be a GFI breaker. It's going to be most likely.
Okay.
So it'll just be a lot more expensive.
Okay.
All right. Overcurrent protection is a form of protection in an electrical circuit that prevents excessive current, usually at a predetermined value. Usually refers to a type of protection designed to deal with instantaneous spikes in current. Okay. So overcurrent protector is more so designed to deal with instantaneous spikes. That would be your circuit breaker, would be an overcurrent protector, right? So big spikes. Overload, so this is a big distinction. Overcurrent, circuit breaker fuse. Overload protection is a protection against a running overcurrent that would cause overheating of the protected equipment. So you got a compressor that is running hot because it's got no refrigerant in it, or because it's got a clogged condenser coil, or because it has way too much refrigerant, or because there's some other problem where it was in a hot pull down for an excessive period of time or whatever. Those are all overload conditions. And those can be either thermal overload that are protecting a device just based on its temperature. For example, if you have a system that's running low charge, it will trip the internal overload, right? But is that compressor overloaded physically? Meaning, is the compressor drawing high current when it's low on charge? Does the compressor draw high current when it's low on charge? The answer is no, because it actually has lighter suction gas coming back to it. So it's actually not working as hard. But it goes out on overload, not because of a current issue, but because of a temperature issue, right? So in many cases, overloads can play this double purpose. And specifically in a compressor, we're looking at that internal temperature of that compressor, and that's what it's tripping based on. It's going to protect against electrical problems, and it's going to protect against other overheating problems. All right, so let's talk about sizing conductors. So what is a conductor?
Wire.
It's just a wire, right? It can be made of copper, it can be made of aluminum, whatever. It's a wire. So these are the factors we got to consider when we're sizing a conductor. First off, what is the circuit amperage? What is the current in the circuit? We have to think about the instantaneous and the continuous. Now again, I'm not going to tell you all the math of how to do this because that's not our job. Our job is not to do complicated math. I'm going to tell you the factors that relate to this so that you can pay attention to outliers. And we'll talk more about what that means. But if you're energizing a circuit that has a motor in it, you know that it's going to have a higher, generally speaking, this isn't always true. Like with an ECM, this isn't true. But in a PSC motor, it is. Or three-phase motor or whatever. You're going to have higher instantaneous current, and then it's going to go down to its continuous. You have to think about the ambient temperature. Is there an abnormal ambient temperature condition that this conductor, this wire, is running through? You have to think about the insulation temperature rating, which is one of the biggest things that we don't consider, and we'll look at that. You have to look at box or conduit fill. This is a very specific electrician thing, and it's a really big thing for electricians. If you have a box or some sort of a raceway, something that you're running multiple conductors through, you have to think about how many are in there, right? Because that heat that builds up in there is cumulative. And what we're really looking to make sure doesn't happen is we're looking to make sure we don't compromise any of the insulation. We don't want the insulation to melt off. Insulation melts off, we got big problems. So that's what we're trying to prevent. Again, remember, NFPA, National Fire Protection, where they're trying to prevent fires. Yeah, they're trying to keep you from getting shocked, but primarily they're trying to prevent fires. That's the main thing here. So things like box fill is important. And then voltage drop. Now, voltage drop from the NEC is a suggested maximum voltage drop. Really, ultimately, with voltage drop, all that matters is, are we delivering voltage? Are we delivering potential to the appliance that the appliance is designed for? So as an example, with a residential AC system, it's going to be very difficult for us to deliver a voltage that's too low. A lot of people, it can happen in a brownout condition where there's like a significant drop, but under normal circumstances, it's going to be really abnormal that we drop low enough because all of our, I shouldn't say all, but most of our single-phase air conditioning systems are rated for 240 volts or 230 volts or 208. Right? So that means they're designed to run at 208 under normal conditions because they're designed to work on two phases of a Y commercial three-phase power supply. So they're rated all the way down to 197. And it's going to be pretty rare that you're going to test voltage at the end of a wire and find that it's less than 197 on a residential application. Now, in three-phase cases, commercial cases with long runs of wire, you very well could. You know, we work on self-storage facilities that have these multiple stories, and that's where starting does become a problem, and it can become a real challenge. But voltage drop is all about just providing the right voltage to the unit while it's running. It's not, the NEC doesn't really care if you have voltage drop, if that voltage drop is within the amount that's acceptable to the appliance you're connecting it to. Does that make sense? A lot of people will say, like, you've got to size to voltage drop. That's not an NEC thing. I mean, it is kind of. They give this suggestion of 4% max, but it's not actually part of the code. It's not required. They want you to size conductors so they're not going to overheat. They don't really care if at the end the voltage is too low, because that's not going to cause a fire. It's just going to cause your appliance not to work, which, you know, they don't really care that much about. Here's a lot of words. Starting current. I'm not going to read all the words, but starting current is when the voltage is first applied to the windings. There's no back EMF, so it's always going to be high initially for those first couple cycles. Running current is what it is once the motor is up to speed and the back EMF or counter EMF is in place, causing inductive reactance, which gets that electrical resistance up and gets your current down. And then locked rotor current or locked rotor amps is if that motor is remaining locked. What is the current it's going to draw if it stays locked? It's not physically moving. 5 to 6 times your regular running amps is what that's going to be. All right, so let's talk about what happened in these cases. Let's start being kind of practical here. So what happened here? Well, first off, what are we looking at? Anybody know?
Motor.
Yeah, we're looking at motor windings here. And so what happens when you see this? What? Quote a new motor. Yeah, well, that's for sure. Somebody let the smoke out. We know that. But what happened here? It's a short. But what came first? Did it short and then that melted the lacquer off the wires, or did the lacquer melt off the wires and then it shorted?
The lacquer melted.
Yeah, the lacquer was most likely compromised and then it shorted. And this is actually an interesting thing with motors, is when you're talking about something that's got all, you know, there's a rotor in there that's spinning around really fast. What would happen if a shard of metal got into that? Maybe bearings came apart or whatever and flew into that winding. What's going to happen to the winding? It's going to compromise the lacquer and it's going to short the winding. So in many cases, mechanical problems cause electrical problems. Right? In many cases, that's what's going on, especially inside of a compressor where everything's in there, right? And something goes wrong, and now it starts bouncing around. You know, maybe it loses its suspension, or maybe there's, you know, metal particles that have gotten in there. That can compromise that lacquer, and then that results in that. But it could be the other way around too. I mean, it's possible. It's possible that there was just like a really high current event or something like that. But again, even then, it's compromising the lacquer first. That's what's happening first. What happened here, do you think? Failed breaker. Okay, that's fairly obvious. What do you think? What do you think happened?
The connection got loose to the panel.
Connection got loose. This is a really interesting one. What happens when a connection gets loose? It can start arcing, sure. Not necessarily. It doesn't always arc. It could be. But you could have a bad connection that isn't necessarily arcing. So what goes on in a bad connection? What does that mean electrically?
You reduce the conductor size.
You're reducing the conductor size, yeah. So it starts to get hot, right? So you're reducing the contact area. And so there's two different sides to this, because a lot of people will say, well, yeah, that creates more resistance, and resistance causes heat. And that's a tricky business, because if you increase the resistance in a circuit, let's go back to Ohm's law. In the video, we'll throw a little Ohm's law up here. What happens if you increase the resistance in a circuit? What happens if the voltage stays the same, which it does, right? Something's going on with this circuit breaker. It's not like all of a sudden the power company is changing the voltage because this circuit breaker is not connected well, right? So voltage stays the same. We increase the resistance. What happens to the current? If you increase electrical resistance, what happens to current?
Down.
Goes down. That means that in your circuit, you have more or less heat overall when your current goes down. You have less overall, right? And this is why it gets kind of tricky when people will, the end of the day, it's not that big of it doesn't really matter. We know we need to have good connection, but the resistance does lead to a problem. But even more than that, the lack of ampacity, amperage capacity through that connection leads to heat in that area, which then leads to more carbon, which then leads to more heat, which then leads to more resistance. So you're going to get a couple things. Before this thing failed completely, whatever was connected to it had a pretty high voltage drop, almost assuredly, because you had resistance in the circuit, which is dropping the voltage, which is actually dropping the current. So whatever's connecting to it's not running well. Until eventually it just keeps that surface contact size just gets smaller and smaller, heat gets more and more, until eventually it melts. Right? So making good metal-to-metal contact whenever you're making connections is key. What other reasons could this happen other than poor contact?
Properly sized.
It's possible, and actually there is one factor here. In some cases, people will try to jam like much too large of wires underneath breakers, and then they end up cutting strands off or whatever, and so that can create a hot spot. That can do it. But more than likely it was just a poor connection. But you could have a breaker that just didn't trip, and it had really high current on it over an extended period of time. That can also happen, potentially. Most likely, just a poor connection. In a lot of cases, it's a poor connection where it actually attaches to the bus. They may have never got it fully snapped in, and so it was just kind of sitting there bouncing on it over an extended period of time.
Or if somebody removed the tabs to put quads in a panel that doesn't accept them.
Yes, somebody removed the tabs to put quads in a panel that doesn't accept them. I would never knew anybody who would do anything like that. Definitely not me. You'll see here, this is referring to sizing table. This is the wrong sizing table. We've selected copper as our conductor type. And you're going to notice we have 3 separate columns. Why do we have 3 separate columns?
Different temperatures
Different temperatures, right?
of your insulation.
60 degrees Celsius is kind of our standard rating, and you'll notice it kind of lines up, right? 15, 20, 30, 40, 55, 70. That's what we're used to quoting. Yeah, for some reason a lot of you think that, but no, it's not. And that's for a 60 degree Celsius insulation on your conductor. And conductors are going to say on them, we'll show a picture here in a second, conductors are going to say on them what the Celsius rating is for that conductor. Why do we usually use this column?
Because that's what Romex says on it.
Because that's what Romex is, right. Romex is a trade name for NM, non-metallic wire, and there's a lot of Romex in residential houses. And so if you're using Romex, you have to use this column. If any part of that circuit is Romex, you have to use this column, right? But that a lot of the, and the more advanced table that comes from the NEC will actually list all the different types of wire for each column. So they kind of make it easier on you, but you can always just look at the conductor and just see what it says. So if you're using Romex, any part of the circuit is Romex, this is the column you need to use. But if you're using 75 or 90, then you can use these two columns. So you could potentially put 25 amps or 20 amps on a 14 or whatever if everything in that circuit is rated at 75 degrees Celsius and it's copper. Now, there's another trick to this, is that everything has to be rated for that, including the termination points. So all your wire nuts, any lugs in your contactor, lugs in your breaker, everything has to be rated that way. And they are. They'll tell you. If you look it up, it'll tell you what the insulation rating is for all of those, what the temperature rating is for all those. Now, also the other caveat is on any tightened connector, there's also a torque rating that you got to follow in order to actually hit that level. So a lot of people just say, hey, look, we're just going to use this column so that way we're safe. We don't have to worry about it. No problem. This is like sort of your safe space. So if that's what you're using and you want to be safe, this is fine to use that column on the left, but it's not always the case. And so a lot of times people will tell somebody they got to rip the wire out and it's not the right size, it's undersized, when maybe it's not. Maybe it's all 75 degrees Celsius or 90 degrees Celsius. In commercial and industrial, you'll also see 105. So it can handle more. If you start to pay attention to wire sizing that manufacturers put inside units, you'll catch on pretty quick that it doesn't really jive with what we have to put in as it attaches to the appliance. They're using smaller wires, and that's because they're using better insulation ratings. But aluminum or copper-clad aluminum, much different. So it starts to, it's not hugely different, but it is different. So you have to pay attention if you have aluminum or copper-clad aluminum. Right, Sam? It ended up being the right size, I guess, didn't it? So I made a real fool of myself, didn't I? I sure did. You also have to think about differences in ambient temperature. So these tables that I just showed you are based on a 30 degree Celsius ambient temperature, which is equal to 86 degrees Fahrenheit. If you have temperatures that are significantly greater than that, or lower than that, you can use a derating or an increase rating. So if your ambient temperature is significantly lower, you can actually use this multiplier to multiply the amount of current that it can go through. Now, again, these are maximum temperatures. Here's another interesting thing. Do we ever run wires through spaces that are more than 30 degrees Celsius? 86 degrees. The answer is yes. So that's another reason that we might want to go ahead and just stick in that left column. Just play it safe. But technically, if we were doing everything by the book, we would have to go and say, okay, what is the maximum temperature of this attic? Let's use this derating factor. I think NM actually there's like a exception or something to NM. So when I say that, I'm not saying that I know for a fact that you're supposed to do that, because in the NEC, there's all kinds of exceptions to every rule. But this is there for a reason. All right, now here's where it starts to get really controversial. It's actually not controversial at all. It's super straightforward, and there should be no controversy. But it's a misunderstanding by electricians that results in this problem. So the saying that electricians repeat over and over and over again from the time that they leave the womb is that the circuit breaker is there to protect the conductor. Right? They'll always say that. The circuit breaker is there to protect the conductor. And so if you have a conductor that is a number 12, if you're going to use the first column, number 12 copper, that means that the circuit breaker has to be what? A 20. That's what they'll say. Because you don't want to run the risk of it having an overcurrent condition and not tripping the breaker, melting the wire, right? Let's take a look here. Minimum circuit amps, 31.4. Maximum circuit breaker, 50. What does that mean? Well, a lot of people will say that means that you could oversize the wire and then put a 50 amp breaker on it if you wanted. That's actually not what it means. And this is not disputed territory. This is just a fact of how it is. You can size your wire based on this number, and you can put in this circuit breaker, which means that the circuit breaker is not protecting the conductor under all circumstances. It is protecting the conductor for a ground fault condition. We'll go back to our conditions here. It's protecting the conductor from a ground fault. It's connecting potentially a ground fault, a major ground fault, and a overcurrent situation where you have an instantaneous spike. So a big problem, shorted compressor, whatever. It's not protecting the circuit from an overload problem, an overload condition. And people will say, well, that's a problem. We'll get into why it's not. So it's okay to put, let's say that we're using the first column, so 31.4, and it's copper. What size wire should we run to that condenser if we're using the first column? 8. All right? 8 is 40. 31.4 is minimum circuit amps. Right? Now, minimum circuit ampacity is what it should say. Actually, this is like an annoying thing because this isn't. What does minimum circuit amps mean? Like the minimum amps the circuit will run. It means minimum circuit ampacity, meaning the circuit must have, the wires connecting this unit must have an amperage capacity that can handle at least 31.4. Now, if we have a 75-degree conductor, then we could use number 10 wire if the entire assembly is rated at 75 degrees. Let's look at this Lennox over here. See, I like Lennox's, this is an old Lennox data tag, they say it better. Minimum circuit ampacity. The minimum amperage capacity of the circuit, 28.6. What size wire can we run to that if it's got Romex running to it? Number 10, right? What size breaker do we put on it? 50 amp breaker. Does the breaker protect the conductor? No, it does not fully. It protects the conductor against these severe spikes in current that happen from a short circuit or ground situation, but it's not going to protect it if the compressor's just running too hard, right? So what protects the circuit if the compressor's just running too hard? The internal overload on the compressor is what protects that. And the fact that that appliance has an integrated internal overload is what allows the manufacturer to put these rating stickers on here. So do you think the manufacturer is putting this on here and they're just kidding? Like they didn't do the math, they didn't already look at the NEC. Of course they did. They're telling you. You can put in, that's the maximum fuse size. Does that mean you couldn't put in a smaller size? You could put in a smaller size. Yeah, only because even a breaker can have an ampacity. But yeah, you could potentially put, anywhere from a 35 to a 50 in there. Now, inspectors aren't going to let you because they don't understand what they're looking at either. So don't even start with them.
You circle it.
But here, we could have a 50 amp breaker on a number 10 wire, and it would be completely allowable by the NEC. Again, go back to the NEC or look at Mike Holt's videos on this if you think I'm crazy, because a lot of people will argue about this, like every single time. All right, these aren't great images here, but if your torque for 75 degrees Celsius is 22 inch-pounds if they're screws and 40 inch-pounds if they're lugs. So in order to get the full 75 degrees out of this bad boy, you would want to make sure that you are actually using your handy-dandy torque screwdriver that you always have in your pocket and torque that bad boy down to exact torque specifications. And if you want to be extra safe, just put a little nylog on it first. That was a joke.
Oh,
Don't do that. Don't do that. So same thing. This is just a zoomed out view, just showing the same thing. But look up here at this conductor. What does it say on it? 90 degrees. So let's say we had these conductors connected to an appliance, but you were terminating them at this contactor, meaning you were connecting the high voltage conductors to the bottom of a contactor, which is often what we do. What is the Celsius rating of that circuit now? 75, right? So if you wanted to make it higher, you'd have to make sure that everything down the line, your disconnect, your breaker, everything was rated at 90. But sometimes that may be the thing to do. Sometimes if the option is between changing all your termination points to something that can handle it or rerunning an entirely new circuit, that may be the thing to do. Now, a lot of people just say, hey, it's no problem, just run number 4 wired everything and then it's no problem. Okay, like sometimes you're talking about applications in multifamily or commercial where there might be multiple floors, it could be a major deal. Sure, if it's just a matter of running a new whip to a breaker panel, well then fine, who cares? Put as big a wire in there as you want. So long as the termination points are designed to accept that correct wire. There's also this weird exception with, I don't know if you remember the whole Bruce Wells thing with the undersized ground in some applications. Is like some weird exception on why even using Romex oversized sometimes could be a code violation. It's a weird exception.
In general, you can't run Romex to the outdoor unit anyway.
Correct. Good point Nathan makes. Do you know why you can't run Romex to an outdoor unit? Anybody know?
Well, you can. It's just against code.
It's against code, yes. The reason why you can't run Romex to an outdoor unit, even if you pull it in Carflex or some other seal type, is because it is not rated for damp conditions. So outdoors, even within conduit, by the NEC is considered to be a damp condition, and you are not allowed to run NM, which is the correct designation for Romex, in a damp condition. So that's why you should either use the pre-made whip or use the whip and pull proper conductors through it. So when a lot of people focus so much on the size of the wire, it's just as important. Here's the main point I'm wanting to make. Just as important as the size of the wire is the insulation rating on the wire. A lot of people go, oh, we'll just put in a bigger wire. Just put in better insulation rating. 6 and 1/2 does the other. They're both performing the same thing. Other than that, bigger wire does serve to reduce voltage drop. Higher insulation rating does not. Higher insulation rating keeps it from melting, but the voltage drop is going to remain the same because the internal conductor is the same. Either way. So if you're trying to beat voltage drop, then you've got to put in bigger wire. But very rarely are we trying to beat voltage drop. So does that make sense on the voltage drop versus the insulation side? It's because they are different, and a lot of people get those confused.
So if you're really close to the wire being the right size, you just wrap it in electrical tape.
I was going to use
Increase that insulation, and you're done. That gets you at least 1 extra amp.
Does that work?
I'm glad you have a microphone on. It's very helpful. What I want to know is, how did that water bottle get balanced on the side of that purlin up there?
Skill.
Like that is really.
That's a
I
question
bet
you should
yourself
ask.
about $100 you couldn't do it. You did.
Did that actually happen? Are you serious?
Wait,
That's the real
what?
story.
Yeah, first try.
No.
First try.
You bet him $100 and then he did it, and did you pay him $100?
Of course not.
Wow.
What's he gonna do?
Poison you. He's very poisony. Wow. Huh. Yeah, he's got his mama's genes. Huh?
If it was like landed upright,
Yeah.
it would be a lot
You should.
better.
Oh, that's what you could say. That's your excuse. I meant upright. I meant on the cap. Yeah, that's. Does it actually have anything in it?
It's filled.
Wow. Okay, I'm gonna have a hard time focusing now. So, like I mentioned, in residential, it's very rare that voltage drop is a real problem, other than 2 reasons. One is that there's a bad connection somewhere, like a significantly bad connection. And the other is if the power company isn't giving you the proper voltage in the first place. And that's not really voltage drop, that's just a power supply problem, right? When you get into commercial, voltage drop becomes much more because you're running these really long conductors. Now, is it possible you could have some really big custom house with a panel on one side, and it's possible. But again, unlikely, because with residential equipment, it's designed to go all the way down to 208 anyway, because it's designed to also work in 3
Maybe if you're
phase.
doing like a sub panel in like an outbuilding or something.
Yep, if you're feeding a sub, maybe you have a sub shop, right? You're making some delicious submarine sandwiches. That could do it. You shouldn't put those in your house. It's not code. The confusion that a lot of people have is they imagine that when there's voltage drop, there's also a hot circuit. So they imagine the circuit's getting hot when there's voltage drop. But actually, that's the opposite. Because go back to Ohm's law. If you decrease voltage, what happens to current? Decreases. Right? Now, in a inductive circuit, it's not completely linear. So a lot of people will say, well, if you run lower voltage to a motor, well, that motor will draw higher amperage. And actually, Nathan and I had an argument about this one time, and you were right. Remember when we were doing all those tests with the testometer and all that?
I like to remember when I'm right about things.
Yeah, okay.
But
That's a sign of really low ego.
But I don't remember
You're
it.
an egoless boy. Anyway, you were right. We actually tested it where we created a voltage drop going into a unit and just kept dropping the voltage lower and lower, and the amperage went lower and lower until the point where the motor stalled completely, and then it went to lock rotor. But that lock rotor was a much lower lock rotor because the voltage was lower. So when you put lower voltage to something, you actually drop its current, and you also drop its capacity. So this is actually an interesting thing. If you pay attention to residential single-phase units, they may be rated at 14, 15 SEER, but when you connect it to a 208 power supply, it actually derates its capacity and its efficiency. So it doesn't work as efficiently, and it also doesn't have the same capacity when you drop that voltage because the motor actually slips more. It's not actually spinning as fast. The synchronous speed actually decreases. It's not a lot, but it's enough that it does affect the capacity and the efficiency of that unit. So the point being that we worry about voltage drop that has to do with length because that results in voltage that's too low to the unit that could cause problems. That doesn't cause overheating. Too long of wires doesn't make things overheat in terms of like the wire or conductor itself. Too small of wires does, and insulation ratings that are too low do, or wires that are run through too hot of spaces, or too many wires run together. Those are the things that cause fire issues, and therefore those are the things that NFPA is concerned with. If you start looking at electrical data, this is from a carrier unit, they make it so ridiculously easy. Like, you do not have to overthink this. So for those of you who are like, the data tag doesn't mean that, well, take a look at this. We got a 4-ton unit here, 48, we go over the MCA, minimum circuit ampacity carrier, ampacity, is 26.1. And you're like, well, what size wire is that? Well, you don't have to guess. They tell you. 60 degrees, it's 10. 75 degrees, also 10. Right? So you're going to run a 10 wire to this. Maximum length at 60 degrees, maximum length at 75 degrees. I don't know why. That's kind of confusing there. I think they've got a little mistake there. But regardless, why are they giving you that maximum length? Are they giving you that because of the NEC? No, they're giving you that maximum length because of their desire to keep voltage drop low to the appliance. If wire is applied at an ambient greater than 30 degrees Celsius, consult table 31016 of the NEC, NFPA 70. The ampacity of non-metallic sheath cable NM, trade name Romex, shall be that of 60 degree conditions. Per the NEC article 3, if other than uncoded, blah, 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 all the stuff that I just said right there in the manual, it says it all, every single thing, right? All the important stuff is right here in the product data for this unit. So it tells you, number 10 wire, what's the maximum fuse or circuit breaker? 40. There's no confusion here. So many people will say, no, you got to put in a 30 because you put number 10 wire. It's incorrect. You can put in a 40. You could put in a 32 if you wanted. But again,
a 32.
you're not going to find a 32. It's a very hard breaker to find. It's very specialty. You got to know people. Or are you going to say, you were going to say something. I guarantee it. You were looking like you were going to say something. I promise. I promise you. Oh, here, it actually even describes, length shown is as measured one way along the wire path between the unit and the service panel for voltage drop not to exceed 2%. So they're trying to ensure that you're not going to exceed 2%. It's actually 4% overall, I think, or maybe it's 3 and 2, something like that. It might be 5, but they're saying between the service panel and the appliance not to exceed that in order to keep your voltage drop 2% or less. I want to address specifically the situation that you had, Sam, because this is a question that comes up a lot. So if you want to loudly describe what it was, and then we can kind of talk through it.
Oh, boy.
Loudly.
There was a large aluminum wire being fed from the outdoor main panel to junction box / breaker box, which then fed from one breaker to another sub-panel, which had its own set of breakers.
And then fed the condenser and air handler, right?
Yeah.
Or something like that. Okay. And the question then becomes like, okay, how do you size breakers and conductors that feed sub-panels that then the sub-panel feeds, and there's multiple things. And here's basically the thing I want to clear up, because I'm not saying that as an AC technician, you're going to do these calculations. I don't want you to. You should hire a professional electrician to do that. So I'm not saying that as an AC technician, you're going to make those calculations, but here's the principle. First off, you don't have to add up all of the breaker sizes and then size your breaker or wire off of that. That's not how that works. I mean, think of convenience outlets as an example. You'll have multiple convenience outlets in your house that are connected to a 15 amp breaker or a 20 amp breaker. We'll say 15 because a lot of houses are, right? So imagine your house. You got a 15 amp breaker, it's got number 14 wire, and it's wired up to all of these outlets. What prevents you from going and hooking a toaster up to one outlet, a vacuum cleaner up to the other, and a space heater to the third, and firing them all up? What prevents you from doing that? Nothing prevents you from doing it. It's just going to trip, right? So it's safe. Why? Why is it safe? It's safe because we're going to go back to what electricians learned since they were little babies, because it's actually a really good thing to know. It is a good rule. The breaker protects the conductor, right? So at that point, it doesn't matter what you hook up. If you exceed for any amount of time that 15 amp rating, it's going to trip. It's going to trip before the conductor is compromised. Make sense? Which is why when we have this special rule in section 440, that special rule is for dedicated circuits, right? We're not taking an air conditioning circuit and then tapping off of it and powering a water softener and then tapping off and putting an RV outlet, next to it or whatever else, right? We couldn't do that because in that circuit is designed specifically for an appliance that has an internal overload, right? That internal overload is there to protect it. The internal overload is what fills that gap in between the wire size and the breaker size. But whenever you have these sort of multiples, it goes back to that same rule. The rule of the breaker protects the conductor, right? So if you're feeding we'll go back here real quick. So let's say the main wire that's going to this sub-panel is a number 4, okay? We'll say it's what was it? What was the wire size? In that case, the aluminum wire.
That was 4.
It was a 4. Okay, so we're going to go to aluminum. That's it. It was aluminum 4. If it's in the 60, category, then that can feed that can have a 55 amp breaker maximum protecting it, because there's multiple things on that circuit. So it doesn't matter what happens if that wire is properly terminated, properly connected, nothing loose or weird, and it's a number 4 wire, and it's got a 55 amp breaker protecting it. If you try to put more than 55 amps on it, what's going to happen? It's going to trip, right? So you can have a sub-panel, because this will come up a lot of times. Guys will see, all right, I got a sub-panel that's being fed by a 60 amp breaker, and it's got we'll say it's copper. It's got number 4 wire, copper going, in between it. But then you go into the sub-panel, and it's got a 60 and a 30 in that. Well, that can't be right, because you got a 60 feeding a 60 and a 30. So long as that conductor is right, then it's fine, because that breaker is protecting that conductor. As far as we're concerned, because it's not our job. We're not the ones engineering the original electrical system, but we're there to be the ones who say, wait, there's a problem. So knowing this helps you say, wait, there's a problem. It doesn't make you ultimately responsible for everything that goes on in the structure. So that's the difference between being an electrician or electrical engineer and an AC guy. We're not expected to design these things from the ground up. We're expected to throw the flag on the field and say, this circuit needs to be rerun because it's a problem. But the point being that in a lot of cases, inspectors and electricians think circuits need to be rerun when they don't, because of these two things. Because of the fact that sometimes you can actually do a little better if you're 75 degrees Celsius, and also because Section 440 gives us this special exemption, and all we got to do is trust the data tag. And if you don't want to trust the data tag, then trust the product data, because it's going to tell you the exact same thing in even plainer language. Conclusion. For AC units, based on Section 440 of NFPA 70, size breakers on your MOCP or your max breaker, max fuse / breaker designation. Those mean the same thing. MOCP stands for maximum overcurrent protector. Maximum fuse breaker obviously just means, and when we say max, it could be lower, all the way down to the rating of the wire. That would be okay, but it'd be likely you'd get nuisance trips. So they allow it to be this higher number because the compressor's a motor, and that motor draws higher current when it starts. We size conductors based on MCA, minimum circuit ampacity. That's the minimum amperage capacity that the circuit needs to be able to handle. So if you've got 23, then you need to have a conductor in there that at minimum can handle 23 amps. That's what that means. Consider termination ratings. Pay attention when we say termination, that just means connection. How are you connecting it on each end? Overfilling wire nuts is something you see people do all the time. That's where, Eric Melly's been falling in love with his thermal imaging camera, and he goes around and finds all kinds of connectors that are getting overheated. And that is actually a really nice use for a thermal imaging camera. Now be careful, those of you who get your little FLIR or whatever it is, whatever brand you get, and you use it the first time and you go into a residential panel, you'll find that some breakers get really hot. Do you know which ones get really hot? Arc fault breakers. Arc fault breakers are just hot by nature because of the internal whatever fancy magic inside of them. It makes them, I'm really prepared to describe the internals of an arc fault, as you can tell. It's the fancy hot magic inside there that makes them just run hot all the time compared to their neighbors. And that's what you use the thermal imaging camera for. It's not so much the absolute temperature, because they're actually not crazy accurate for that anyway, because of emissivity. So depending on the surface, there's going to be some slight variation. But if you go breaker to breaker, it should all be pretty similar, especially if they're all running under load. But all of a sudden, when you look at this one whole half of a panel, this is the first time when Travis White got his thermal imaging camera the first time. He's like, one whole side of the panel is really hot and the other side is cool. And we thought it was like some sort of phase thing. We were trying to figure out what it was, but it was just one side of the panel was full of arc fault breakers and the other side was full of standard breakers. So it's something to watch out for. Consider your termination ratings, disconnects, contactors, wire nuts, breakers. If you're going to try to use a higher column, just keep in mind all those terminations, all those connections have to be in there. Consider ambient temperature. So especially in things like factories or places that could be really, really hot, think about that. If you have really high ambient temperatures, you're going to want to look at your derating columns and derate those conductors. Run bigger conductors, larger conductors. Consider fill, so you can't just jam in an infinity number of wires through the same conduit or through the same raceway. They don't like it.
Just because it fits doesn't mean that it ships.
Yep, just because it fits don't mean it ships. And then conductor length, and why do we consider conductor length? Voltage drop. We consider conductor length for voltage drop. And again, 2% is that, from your final disconnect or from your final connection point to the appliance. That's where you'd want to see maximum 2%. Now, quick question. Under what condition do you have to measure voltage in order for voltage drop to mean anything? Under what condition do you have to measure your voltage in order? Full load, right? The thing has to be running full tilt. So that would mean if you have a system that has highly variable load in it, like sometimes it's under much more load than others, you have to make sure that you're at maximum load. If it's a multi-stage unit, that means it's got to be at high stage. If it's something like a refrigeration unit and you really want to know you're having some intermittent problem, run it right out, run it through a defrost and look at with the compressor under full load when it's coming in out of a hot pull down. Look at what the voltage drop is then, because that's when it's going to show up, when it has the highest current. It's just like water pressure. If you test your water pressure with nothing running in the house, you're always it's going to look like it has good pressure. It's dynamic pressure. It's pressure when you have things running, like a shower or a bath or whatever. That's when you're going to see that pressure drop. The same thing is true with electrical. You got to measure voltage under load. Voltage is doesn't have a lot of point in measuring it without a load. That's also where you see ghost voltages and things like that. That's why you see that, is that you may have just barely any current at all, maybe just a hair of a wire's connecting, and you'll see these voltages show up, but they're not effective to actually run a load when you try to energize something with it. Watch out for aluminum conductors. If you're trying to do calculations or you're trying to determine if your wire's the right size and you're not paying attention to whether it's aluminum, that's a problem. Also, aluminum conductors often require regular maintenance in order to make sure that they don't begin to corrode. Also, if you're going to use any connector on aluminum, make sure that it is rated for an aluminum connection or an aluminum to copper connection, because they're not all rated for that. You get corrosion, you get galvanic corrosion between dissimilar metals over time, and so aluminum is really, I think the technical word is it's really stinky. Make good connections. Make sure all of your connections are tight. Really high critical connections, we really should be using a torque wrench or screwdriver. That's not going to be your typical residential. I mean, come on, nobody's doing that. But in more mission critical environments like industrial, heavy commercial, where you need things to run in very, vibration heavy, high temperature environments, using a torque screwdriver and a torque wrench to really make all of your connections that required is a good idea. Also keep in mind, do not confuse inch pounds with foot pounds, because you will really break some stuff off if you try to set it to 22 foot pounds rather than 22 inch pounds.
Also, in reverse, it will be very loose.
Also, in reverse, it will be very loose, yes. Thermal imaging is a great method to check connections under load. Again, thermal imaging doesn't mean anything if it's off, right? It's got to be running at full load, and it's best used as a comparative. So thermal imaging is great when you're in a rack house with a bunch of compressors that are running, and you can look at the differences in temperature and the differences in of their connection point temperatures, because you're comparing them to each other. Looking at the absolute readout on a thermal imaging camera is the same as an infrared. They're not super accurate as an absolute temperature readout, but they're very helpful when comparing things against each other. And then consider start current on inductive loads, which means that just when you're working with an inductive load, a motor load, just remember that your start current is going to be higher. Now, obviously, if you're following the manufacturer guidelines, then you're safe. It's when you get into really big stuff with built-up systems that it isn't engineered, that now there's quite a bit more engineering that has to go into the design of the electrical system. Because Hill Phoenix doesn't have like this manufacturer data plate on the entire rack. Like, this is a little more variation, and so there is more engineering and design involved. Now, as a technician, you're not generally going to have to even think about that, but you want to know enough about it to be able to, again, throw the flag on the field and say something's not right here. This doesn't seem right. Because you will catch, everybody makes mistakes, even on the design side. Cool. Any questions? Yes.
Why does an arc fault breaker run hotter than the other breakers?
The arc fault breaker runs hotter because it has current that's actually doing work inside of that breaker. It's doing something in there. I think there's like a electronical microprocessor in there, and it heats and it makes hotness inside. And hot goes to cold. So there you have it. Bada bing, bada boom. All right, so that's basically all you need to know. I went ahead and shared this entire thing with all of you in case you want to review it later, but it really is that simple. If you know to look for these things, and you know that there are specific exceptions, and if you pay attention to Section 440, NFPA actually has an app for both Apple and Android. It's kind of old school, but it is nice for reference. It's $98, which is kind of weird, but for an app. But compared to the entire NEC book, it's still less expensive than that, and you can actually search it based on keywords, which is kind of nice.
Plus, it fits in your pocket way better.
It does fit in your pocket way better than the NEC book. So yes. So I do suggest for those of you who really get into this thing to have that some sort of reference to that. Again, your average technician, you can look this all up online. I have an article about overload specifically. So if you go to the HVAC school app or to my site and just type in the word overload, there's an article specifically about this. Because really, the reason why we have these exceptions that our breaker size doesn't have to protect our conductor is because the overload in the compressor or the motors is protecting the conductor. So that's the reason why. And so understanding overload is really a key to that. And in fact, our overloads are even more than that, like we mentioned, because not only do they protect for an overcurrent condition, they protect for an overheat condition as well. Now, you do have motors, and you'll see them in commercial all the time, where those motors do not have an internal overload. They're just relying on the overload built into the starter, and that's the only overload. So you will see that. Or even in small appliances, you may have an external overload that's mounted on your compressor terminals. But there's still going to be some form of overload. There's going to be some method for independently protecting that device and the conductor that feeds it. All right, thanks everybody. Appreciate you.
Thanks for watching our video. If you enjoyed it and got something out of it, if you wouldn't mind hitting the thumbs up button to like the video, subscribe to the channel, and click the notifications bell to be notified when new videos come out. HVAC School is far more than a YouTube channel. You can find out more by going to hvacrschool.com, which is our website and hub for all of our content, including tech tips, videos, podcasts, and so much more. You can also subscribe to the podcast on any podcast app of your choosing. You can also join our Facebook group if you want to weigh in on the conversation yourself. Thanks again for watching.